Hello everyone. In this video, we're going to discuss t-tests and the five-step method for hypothesis testing. My name is Fred Rispoli. So in particular, we're going to talk about one sample, two sample, and pairwise t-tests. As we discuss the t-test, we'll use the five-step method for running hypothesis tests. The problems discussed in this video are from the textbook Probability and Statistics for Science and Engineering with examples in R by Hongshik Han. To begin with, let's start with a hypothesis testing roadmap for continuous data. In particular, we're going to look at the part with normal data. And let's consider the samples that are possible. It's possible to have just a one sample test, and that would lead to a one sample t-test. This is what we're going to cover in the video. A one sample variance test. We will not cover these, but perhaps in a later video. When there are two or more samples, the first step would be to test to see if there are equal variances. And if there are, we could run a two sample t-test under that assumption. If variances are not equal, we could also run a two sample t-test, but the method is slightly different with respect to the standard deviation. We will not do one of these in this video, but we'll cover a two sample t-test. And the third possibility is when your data occurs in natural pairs. In that case, we run a paired t-test. Okay, so let's start with our first example, a one sample t-test. Suppose that a manufacturer wishes to set a standard time required by employees to complete a certain process. Times from the 16 employees have a mean of 4 hours and a standard deviation of 1.5 hours. And suppose the manufacturer claims that the average time is 3.5 hours and wants to test if the mean processing time exceeds 3.5 hours at the level of alpha equals 0.05. We'll assume the completion time data is normal. We'll run our one sample hypothesis test, find the p-value, and use the five-step method. All right, so step one would be to identify the hypotheses. So our null hypothesis is that the population mean mu is equal to 3.5 hours, and we'll identify that as the claim. The alternative is that mu exceeds 3.5 hours. The second step is to identify the significance and the test to use. Well, we were given that alpha is 0.05. We'll note here that our sample size is 16, our sample mean is 4, sample standard deviation 1.5. We know the data is normal. So whenever n is small, as in less than 30, and the population standard deviation is unknown, and we're interested in testing about means, then it's appropriate to use a one sample t-test. Step 3 is to identify the test statistic and the rejection region. So our test statistic here is t's x bar minus mu 0 divided by the sample standard deviation over the square root of n. And the rejection region is determined from the t-distribution table. When we look up in the table, alpha is 0.05 and degrees of freedom is 15, we get 1.753. So let me just jump ahead to the table and let's identify that. So here we use this number in the red circle. Notice the degrees of freedom rho is 15 here and alpha is 0.05. So this tells us when to reject the null hypothesis. The idea is if our test statistic is greater than 1.753, we could think of it as this value here, then we will reject. Okay, so step 4 is to calculate the test statistic and give the decision about whether to reject or fail to reject the null hypothesis. So when we substitute values into this formula using a sample mean 4, mu0 is 3.5, so we get that from here. The standard deviation, S, is 1.5, so we put that here. And then this is the square root of n, 16. Simplify this. Okay, it may be a good idea to pause the video and work this out. We should get 1.333. Make a note that this is less than 1.753, so therefore we do not reject the null hypothesis. Remember, over here this tells us we reject if t is greater than 1.753. So here our value for t is 1.333. Okay. In step 5, we give the p-value and the practical conclusion. So if we're limited to just the t distribution table, then we try to obtain a bound. The way we obtain the bound is we make a note that our test statistic was 1.333. So we go back to the chart. Degrees of freedom here is 15. So we're looking at this row. 1.333 would be sort of to the left of this 1.341 value. Okay. We know this column is the alpha is 0.10. So that would be the area in this tail. And we're still to the left. So our bound would be just above 0.10. Okay. So we get something like p is greater than 0.10. Okay. If we wanted a more precise bound, then we could use technology, the R language, or perhaps Minitab. I'll show you the Minitab in a couple of seconds. But we could finish this step over here with a summary sentence. The data supports the claim that the mean time is 3.5 hours at the alpha equals 0.05. So the data supports this claim right here that the mean actually is equal to 3.5. Okay, so just another minute on this example. If we use Minitab, we could create a distribution plot to understand what the p-value is. So here the p-value represents the probability that t is greater than 1.333. And Minitab outputs this over here. We get 0.1012. So remember our bound was just p is greater than 0.10. So that was actually a fairly good bound. It turns out it's just a little bit more than 0.10. Okay. And I put in this black line here. This black line represents our critical value, 1.753. So everything to the right of this black line would be the rejection region, and you could see 1.333 is not in that rejection region. So this just gives us a little bit more information and confirms what we did. In our next example, we're going to take a look at a two-sample t-test example. So suppose that the following table shows summary data on mercury concentrations in salmon. The unit is parts per million from two different areas of the Pacific Ocean. So we'll just call them Area 1 and Area 2. You could see that the sample means do look fairly close, right? Area 1 has a sample mean 0.0860. Sample 2, 0.0884. So they do look somewhat close. The question is this difference enough to be considered statistically significant? These are the sample standard deviations. So our formal question, does the data suggest that mercury concentration is higher in salmon from area 2? Okay. Assume equal variance, and we'll use a significance of alpha equals 0.05. Okay, so we start to think of the 5-step method. Step 1, identify the hypotheses. So now we have mu1 is equal to mu2. That's our null, and the alternative is mu1 is less than mu2. So this is telling us that the mean from area 1 is less than the mean from area 2, and we identify that as the claim. Step 2, to identify the significance and explain why you're using whatever test you choose. So here we know the significance, 0.05 given. I have sample sizes of 15, both samples. That's considered small. We also know the data is normal. So these are the conditions for a 2-sample t-test when we want to compare means. The test statistic is given by t is equal to x bar minus y bar over a pooled standard deviation times the square root 1 over m plus 1 over n. There's a formula for the pooled variance given down here. So we could substitute in these values that were given on the previous slide. And you can see we get this very small number, but beware because we have to take the square root of this variance to get the standard deviation. And this number does get larger when you take the square root. Next, we want to identify the rejection region by looking up the critical value. Okay, so notice that it's a one-tail test and it is a left tail test. So we have to think in terms of the left side of our distribution curve. The degrees of freedom is going to be 15 plus 15 minus 2, so 28. Alpha is 0.05. So when we look at a table, the normal distribution table, you could see that the critical value that defines the rejection region is this 1.701 in the red circle. Okay, we get this by noticing the degrees of freedom row is 28 and the column is 0.05. Okay, so that's where this is coming from. We use a negative again because it's a left tail. So the idea is when we calculate the test statistic, if our answer out of this is less than minus 1.701, then we will reject the null hypothesis. Okay, so continuing, we calculate the test statistic and we work this out. Again, good time to pause the video, try to work out this number. You should get minus 2.186. This does happen to be less than minus 1.701, so therefore we would reject the null hypothesis. The p-value, okay, if we must use the table, okay, for example, in let's say testing situations, if you need to come up with an estimate for the p-value, okay, what we have to do is keep in mind minus 2.186 and go to the table. Okay. The values for the t-distribution are only given for the right tail, but we have to keep in mind we're working on the left tail. So we think in terms of 2.186 here. 2.186 is between these two values, right? We stick with 28 degrees of freedom. That's where we looked up this critical value. It's the same row. 2.186 between these two values. So I go up here, and we know the p-value is between these two. So the p-value is between 0.01 and 0.025. So that would give us a good estimate. You could see if we want to confirm this decision to reject the null hypothesis, this p-value we know for sure is going to be less than 0.05. So that would tell us that p is low, and when p is low, we know we reject the null. The null must go. Okay, if we wanted an exact value, then we could use technology to get the p-value, or actually run the test for that matter. I ran this in Minitab, and Minitab gives us a p-value of 0.01867. Okay, to get this, we use an x value of negative 2.186, and we find the left tail probability for this value. We get 0.01867. This black line represents the rejection region. So the rejection region would be everything to the left of this black line. Okay, the black line was at minus 1.701. Okay, so finally we could say that the data supports the claim at the alpha equals 0.05 level. Okay, and now let's take a look at our third example for this video. This example illustrates the paired t-test. So let's suppose that a manufacturer of furniture claims that the company's new model of bookshelves is easier to assemble than the old model. To test the claim, 7 people were assigned to assemble the bookshelves from each of the two models. Below are the times in minutes they needed to assemble the bookshelves. So you could see person 1 took 17 minutes to assemble the old model, but 15 minutes to assemble the new model. Person 2, 22 and 19, and so on. We want to test if the mean assembly time for the new model is shorter than that of the old model using alpha equals 0.05. So notice how the data occurs in natural pairs over here. Okay, each person assembles both models. Okay, so this will have the effect of a lower standard deviation compared to the case if we treated this as one sample and this as two samples. Okay, so our first step is to look at the differences. You can see here, these are the differences in assembly time. 17 minus 15 gives us the 2. 22 minus 19 gives us the 3. So now if we were to take the average of these differences, we get d bar. Okay, turns out to be 1.57. And the standard deviation of the differences is 0.976. So step 1, we identify the hypotheses. We state the null hypothesis here as delta equals 0. So delta is used to represent the population difference. Okay. The alternate hypothesis is that delta is greater than 0. Okay. And this would be the claim here. Step 2, okay, we're given alpha is 0.05. We know n is 7. So here we count the number of pairs. There's 7 pairs. And d bar is 1.57. The data is paired, so we'll use a pair t-test. Okay. The test statistic looks like this. T is equal to a d bar divided by our standard deviation over the square root of n. The rejection region here is obtained using 0.05 for alpha, and degrees of freedom now is 6. So if we look this value up, let's see, I have the table over here. Degrees of freedom 6, alpha is 0.05. We would get 1.943. So that's where this number comes from. It comes from the t distribution table. All right, step 4, we calculate t, so we substitute values into the formula, work it out, and we get 4.256, which is much greater than the critical value 1.943, so therefore we reject the null hypothesis. Now, the p-value, okay, if we try to use the table, we need to keep in mind 4.256, degrees of freedom 6. So now we go over here. This is the row. We're looking for 4.256. We notice this number, 4.256, is even greater than this number, so it puts us somewhere over here. I look up, I see alpha is 0.005 as far as this goes. So what we can say here is that our p-value, notice how these numbers are going down, our p-value will be less than 0.005. And that's what we really want here. We want an upper bound on the p-value. So p-value is less than 0.005. If we were to compare this to alpha, 0.05, it's much, much less, which confirms that we would reject the null hypothesis. If we wanted an exact value, we could use technology and get the probability that t is greater than 4.256 is 0.0027. Okay, and we could see that once again using a Minitab distribution plot. When we enter the x value of 4.256, that's the test statistic, our p-value 0.002672 is the output from Minitab. So to summarize, we could say the data supports the claim that the new bookshelves are easier to put together at the level of alpha equals 0.005. All right, so remember, we're rejecting the null, so the data does support that this delta is greater than 0, which in turn implies the new models do take less time to put together. Okay, so this concludes the video. Thank you for watching.